All right, everybody, welcome to video 3 from section 1.2. We're going to see how echelon form helps us or is related to solving linear systems. So let's get right to it and solve this linear system. Okay, as always, the first thing we want to do is get the augmented matrix. So let's do that. 2, 6, 3, 1, 5, 0, 0, 1, -1, -5. 2, 6, 2, 0, 2. Okay. So we've got a non-zero entry in this top left corner. So that'll become our pivot, and we'll use this value to make zeros below it. So let's do what? Row 3 gets sent to row 3 minus row 1. That hasn't changed. Or has that? And now we've got 2 minus 2 is 0, 6 minus 6 is 0, 2 minus 3 is -1, 0 minus 1 is -1, 2 minus 5 is -3. Okay, and so we've got our zeros below our first leading entry. So we look for our next leading entry. Boom, 1. Okay. So then let's go pick on row 3 again. Take row 3 to row 3 plus row 2. So our first row hasn't changed at all, nor has our second row. Poor row 3, just taking a beating. Okay, -1 plus 1 is 0, -1 plus -1 is -2, -3 plus -5 is -8. Okay, so we have our row echelon form. If we want to get reduced row echelon form, we now need to start with our lowest pivot, scale it back so that it's equal to 1, and then crush everything above it. So let's replace row 3 by -1/2 row 3. 3. That'll give us a 1 in the leading term. -1, -5, 0, 0, 0, 1, 4. And now we can use this 1 to clear the spaces above it. So let's do this a little quicker. We'll replace row 1 by row 1 minus row 3. Let's at the same time replace row 2 with row 2 plus row 3. Okay, 2 and the 6 haven't changed, neither has the 3. We're just taking row 1, subtracting row 3. So 1 minus 1 is 0, 5 minus 4 is 1. 0 and 0 hasn't changed. We've got a 1 there. We're adding everything. -1 plus 1 is 0, -5 plus 4 is -1. Okay, and row 3 hasn't changed. Okay, so we've cleared off the entries above our first pivot. We'll look at the next rightmost pivot. Is this one? It's already 1, so we can just clear off the 3 above it. So we'll replace row 1 with row 1 minus 3, row 2. 2, 6, 0, 0. Okay, this is the only one we need to think about. What? This is 1 minus 3 times -3. That's 1 plus 3 is 4. 0, 0, oops. 0, 0, 1, 0, -1, 0, 0, 1, 4. Okay, so now we've cleared off above the second rightmost pivot. All we need to do now is scale this first row and we're all set. So we'll send row 1 to half row 1 to get back 1, 3, 0, 0, 2, 0, 0, 1, 0, -1, 0, 0, 0, 1, 4. And what this tells us, so this is our reduced echelon form. And one of the reasons we like this is because this is giving us this algorithm we've found to find row echelon form is giving us a solution to our linear system, basically, or as close to a solution as we can get. So this represents, the corresponding system, linear system, I should say, Squeeze the word linear in there. Corresponding linear system is exactly what? It'll be x1 plus 3x2 is equal to 2. X3 is equal to -1, and x4 is equal to 4. So, okay, it isn't just like, here's exactly the solution, but it's very close to that. It's saying we know exactly what x3 and x4 are. And if we know what x2 is, then we know what x1 has to be too. But in particular, it's not giving any restrictions on what x2 is. So let's write some of this down. I might need a little more room here. That's fine. Okay. So since x1 corresponds, to a pivot position, and what I mean is, since we're getting this x1 that comes from this is one of our pivots, and it corresponds to x1. X2, there's no pivot in column 2. So since x1 does correspond to a pivot position, and x2 does not, we say the solution is that x1 is equal to 2 minus 3x2. X2 is anything. We'll leave a space there for a second. X3 is -1, x4 is 4. Or x3 can be anything. Be anything. Okay, and in this case, the correct nomenclature, instead of just saying x2 could be anything, is that x2 is a free variable. So maybe let's cross this out, just say x2 is free. Yeah, so since there's no pivot in the x2 column, we say x2 is a free variable. In other words, any value you choose for x2, gives a complete solution to our system, to our linear system. So for example, if we choose x2 to be 0, then we get the solution x1 is what? 2 minus 3 times 0, so x1 is just 2. X2 is still 0. X3 is forever -1. X4 is forever 4. Okay, and you should check that this satisfies the original system up all the way up here. So plug in the correct values for x1, x2, x3, and x4. And similarly, there's nothing special about 0. So for if x2 is 100, then x1 is supposed to be 2 minus 3 times 100. So that's what, -298. X2 is still 100, like we said. X3 is forever -1. X4 is forever 4. So check these are solutions. To our linear system. Okay. And so this is an example where our linear system doesn't just have a solution, it has infinitely many solutions. It's got one solution for every selection of a number for x2. Okay, let's do another example. Okay, and once again, yeah, the more comfortable we're getting with row operations, the more compact I'm going to make the notation. So maybe let's try seeing how compact we can make it. So we get our augmented matrix 2, 6, -3, 1, 1, 4, 1, 0. Oops, let's give ourselves a little more space, separate our rows and columns. -4, 0, 6, 2. Okay, so we use this tilde to denote row equivalence. And you'll notice, yeah, things like, we'll just swap out row 2 and row 1. 1, 4, 1, 0, 2, 6, -3, 1, -4, 0, 6, 2. And now what do we do? Now we can use this 1 to crush the terms below it. So maybe we'll take row 2 and send it to row 2 minus 2 row 1. We'll take row 3 and send it to row 3 plus 4 row 1. And the little convention I'm using here is that the row that's changing is always the first one mentioned. So this is row 2 goes to this thing. This is row 3 goes to this thing. Okay, so then what's happening? Our first row hasn't changed at all. Now we're doing row 2 minus 2 row 1. So this becomes 0. 6 minus 8 is -2. 3 minus 2 is -5. 1 minus 0 is 1. Sorry, that 10 is, it's not a 10. This is, there we go. All right, and now 4 plus 4 times 1 is 0. 0 plus 4 times 4 is 16. 6 plus 4 times 6 is 10. 2 plus 4 times 0 is just 2. Okay, so we've eliminated the terms below our 1, and we should take this next term to be our next leading term. Okay, so then we can get rid of row 3 by adding what? We want 8 row 2. Make sure that checks out. Row 2 won't change at all. And our row 3 becomes 0, 0. Let's see, 10 minus 40 is -30. And 2 minus 8, sorry, 2 plus 8 is 10. Yeah, great. Okay, so now we have our echelon form. Nice cascade from right to left with zeros beneath. Let's get a 1 in all of our leading, or let's get a 1 in this lowest leading entry and this row is above it. So we'll go to, oops, -1/30 times row 3. 1, 4, 1, 0, 0, -2, -5, 1, 0, 1, -1/3. And now we can take row 2 and add 5 row 3 and take row 1 and subtract row 3. So 1, 4, 0, 1/3. 0, -2, 0. Here we go. What? Row 2 plus 5 row 3. Okay, so we want 1 minus 5/3 is 3/3 minus 5/3 is -2/3. Good. 0, 0, 1, -1/3. I have the solutions written down ahead of time. I just can't. I want to do it in my head. It's hard to read something. Okay. I am prepared though. I swear I'm prepared. I might need some more space. We're pretty close though, aren't we? So we've cleared off above everything above here. So let's scale our next leading term. I think we'll be okay. scale this next leading term. So we want -1/2 row 2. And we're going to get what? 0, 1, 0. What? If we divide it by -2, we should be getting 1/3 again, right? Nice. 0, 0, 1, -1/3. Okay, and then finally we want row 1 -4 row 2. 1, 0, 0. Doesn't look right. Oh yeah, so 1/3 minus 4/3 is -3/3 or -1. Okay, 0, 1, 0, 1/3, 0, 0, 1, -1/3. Okay, so we have our row echelon form. And this is exactly what we want on day 1 was a system that looks like this, because this is saying x1 is equal to -1, x2 is equal to 1/3, x3 is equal to -1/3. It's exactly the solution. Here are the numbers that work. Here are the only numbers that work. This is our unique solution to our linear system. This is what we were expecting in high school when we had a system of 2 equations and 2 unknowns. We wanted a value of x. We wanted a value of y. That's what we were looking for. Okay, so our solution. This is giving us a solution. So no free variables here. But no tears over no free variables. That's just how life is sometimes. Okay. Right, and so next we have, let's pull up the slide here. We can summarize that, right? The information that we're able to glean from reduced row echelon form. My phone is ringing. I'm sorry. Okay. Let's turn the ringer off, and that way this won't happen again. Okay. So let's see what this theorem says. Linear system is consistent, so has a solution, right? Has a solution if and only if the rightmost column of its augmented matrix rightmost column is not a pivot column. Okay, pivot column. In other words, the reduced row echelon form does not have a row. That looks like all zeros and then some non-zero number in the very last column. So for a non-zero number b, right? We saw in a previous video, if you have a row like this, this means 0 is equal to b. Like no x1s and no x2s all the way up to no xn is equal to b. So 0 is equal to b just isn't true if b is non-zero. So that's the situation where you're inconsistent, you have no solution. And so as long as so basically the first part of this theorem is saying, as long as you don't have something saying 0 is equal to something non-zero, then you must have a solution. The only way to have no solution is if you've got a row that's trying to convince you that the 0 is equal to something non-zero, or the 0 is equal to 1, for example. Okay, so then the next part of this theorem says if there is a solution, so if your linear system is consistent, there are only 2 possibilities. We mentioned this in the very first video, I think. The 2 possibilities are there's a unique solution or there are infinitely many solutions. And in fact, the reduced row echelon form tells you this too. So if let's write this down. if a linear system is consistent, does have a solution. Then the solution set is either a unique solution, and this is the case when there are no free variables, or infinitely many solutions. And this is the case when there is one or more free variables. Okay, so we saw examples of unique solution. Above here, we saw an example of infinitely many solutions, what they looked like. This form, x1 is some function of x2. x2 can be anything. x3 and x4 are fixed. And we've seen examples in maybe the last video of 1.1 where there's just no solution, where we ended up having a row that looked like zeros with a 1 here. And like, of course, there's no solution. There's no number, no values of x and y that are going to make, or x1 and x2 that are going to make 0 equal to 1. Okay, that's a wrap on section 1.2. I'll see you all next time.